Hello guys, I am Saloni Kumari and I am second year PhD scholar in Department of Chemistry IIT Kanpur. I have completed my bachelor's from Ramdas College, Delhi Universities, followed by master's from IIT Kharagpur. So in this online platform, I'll be taking classes for class 11 students. So only chemistry, and so I'll be starting with structure of atom. I hope that these video lectures will be helpful for you guys. So from the Dalton's atomic theory, we already know that atoms are the ultimate particles of matter. So Dalton has said that atom is unbreakable. So the you can break the matter up to atom. Atom is unbreakable, so atom is the ultimate particle of matter. So this is the Dalton's atomic theory. This theory was able to explain certain things also, like it was able to explain law of conservation of mass, law of constant composition, and law of multiple proportion. But this thing was not true because it was unable to explain certain experiments. So an experiment was carried out like glass or ebonite. When you rub it with silk or fur, it generates electricity. So this thing we also have done in our home while playing or doing certain things. So if you rub any silk cloth with a glass or ebonite, then you will see that it generates electricity. So this means that atom has some charged entity inside it. So this means that atom is not the ultimate particle of matter as stated by Dalton. Rather, it can be breakable. It can be breakable. Okay. So in the 20th century, many different kinds of subatomic particles were discovered, which we will be studying in this in the future in the further slides. Electrons was discovered by Michael Faraday, and actually this guy carried out one experiment using a cathode ray tube. This tube is made up of glass and it contains two metal. One is and both the metals are called the electrodes. And actually he observed the electrical discharge through the gases which is present inside this tube, and observed some very interesting observations. So this actually for this experiment, very low pressure of the gas is needed and very high voltage is needs to be applied. So he adjusted that low pressure using the vacuum, and he applied high voltage using batteries. So when sufficiently high voltage is applied across the electrodes, the current starts flowing from through a stream of particle moving in the tube. So the current starts flowing from here. Then we know that the electron starts flowing from the negative terminal of the battery. So this electron starts flowing when the high voltage is applied. So which actually so because of this, a stream of particle was observed to like move from this negative terminal, that is the cathode, to the positive terminal, that is the anode. So in the second experiment, in order to prove that there are some particles, what he did is that he used the perforated anode. Initially it was not perforated, but in the second experiment he used the perforated anode and also coated this surface with a phosphorescent material, that is the zinc sulfide. So when again he carried out the same experiment, and this stream of particles that was which started its journey from the cathode and was moving towards the anode, as since the anode has had perforations, so it crossed the anode, and here, that is the fluorescent material, it hit that fluorescent material, and that is why some kind of phosphorescence was observed. So from this experiment, Michael Faraday uh, confirmed that there is some particles, some charged particle that is traveling from the cathode to the anode. So and named it as the cathode rays. So the cathode ray started from the cathode and moves towards the anode. Okay. So there are some characteristic features of this experiment. So in this particular experiment, he did not put some electric and the magnetic field. So in the absence of the electric and the magnetic field, all of these rays travel in a straight line. Okay, and also in the absence of the electric and magnetic field, the behavior of the cathode ray are like that expected from negatively charged particles, that is named as electrons. So in the like in the next slide, we will be dealing with the experiment which actually indicated that in the absence and in the presence of electric and magnetic field, what is the behavior of this cathode rays. So this is the apparatus for determining the charge to mass ratio of electrons. As I told that when they applied the electric and the magnetic field, they observed some deflection. So this is that apparatus which showed them that. And also in the absence of any kind of field, the cathode ray was found to go straight without any deflection. So using this experiment, J.J. Thomson found out the ratio of the electric charge to the mass of the electron. So by applying the electrical and the magnetic field perpendicular to each other, as well as to the path of electron, so this is the magnetic field, and this is the blue and the yellow one is the electric field. Okay, so these two are perpendicular to each other, and also it is perpendicular to the flow of the cathode ray. So that is the experimental setup. And so this guy J.J. Thomson observed the amount of deviation of the particle from their path in the presence of the electric and the magnetic field. So he observed that these deviation depends upon the magnetic of the negatively charged, the negative charge on the particle. So more the amount of the negative charge, more will be the deflection, and also the mass of the particle. Lighter the mass, greater is the deflection. These are the simple logistic things. And also this deviations actually depends upon the strength of the electrical and the magnetic field as well. So by using this experiment and by carrying out the accurate measurement on the amount of deviation observed by the electrons on the electric field strength or the magnetic field strength, Thomas was able to determine the value of E upon ME, which is equal to 1.758820 into 10 to the power of 11 coulomb per kg, where E is the mass of the electron in kg, and ME is the magnitude of charge on the electron in coulomb. And this charge is negatively charged because of the electrons. These are negatively charged particles, as these deflections was found according to the particles that are negatively charged. Further, R.A. Millikan, in the time period of 1906 to 14, carried out an experiment which was known as oil drop experiment, by which he discovered the charge on the electron to be minus 1.6022 into 10 to the power of minus 19 coulomb. And by using the Thomson's value of E upon ME ratio, which we just studied in the last slide, so the mass of the electron, that is the ME, was calculated by using this formula and was found to be 9.1094 into 10 to the power of minus 31 kgs. So after the electrons was discovered, discovery of protons took place, followed by neutrons. So this guy E. Goldstein carried out a similar electrical discharge, which was carried out in a modified cathode ray tube, which led to the discovery of particles that was carrying positive charge, and he named it as cannon rays. So the the negatively charged particles was called as the cathode ray, and the positively charged particles was called as the canal rays. So these are the few characteristic feature of these rays which actually helped Goldstein to come to a conclusion. So these positively charged particles depended upon the nature of the gas present in the cathode ray tube. So basically these were nothing but the positively charged gaseous ions. So this is unlike that of the cathode rays, because in those cases that negatively charged particle did not depend upon the nature of the gas. But here for positive, these canal rays actually depended upon the nature of the gas present inside the cathode ray tube. and the charge to mass ratio of these particles was found to depend on the gas again, which was unlike to that of the cathode ray. Some of the positively charged particles carry a multiple of the fundamental unit of electrical charge. So these charged particle, so these positive charged particle actually has the fundamental unit of charge same to that of the electron, just the positive version of it, and some particles had a multiple of it, that particular charge. And the behavior of the particle in the electrical and the magnetic field was found to be just opposite to that observed for the cathode rays. So this guy Goldstein termed proton, this actually coined this term proton, and it was given to the smallest and the lightest positive ion, and which was observed from the hydrogen. So in 1932, so this guy Chadwick discovered neutrons. So after the discovery of electrons and protons, a need was felt for the presence of electrically neutral particle as one of the constituents of atom. So this scientist Chadwick discovered such particle that was neutral, and he discovered it by carrying out one experiment by bombarding a thin sheet of beryllium by alpha particles, so which resulted in emission of electrically neutral entities having a mass slightly greater than that of protons. And Chadwick named these particles as neutrons. So for now, we already know that the Dalton's individual atom is composed of some subatomic particles which carry positive and negative charges, and also some neutral particles are also present. So now there are various atomic models that has been proposed after the discovery of the subatomic particles, and we are going to discuss two of them. The first one is the Thomson model of atom. So this is what Thomson's model of the atom looks like. So it has a spherical shaped atom is there, which is positive in nature. So it consists of a positive sphere with a radius approximately equals to 10 to the power of minus 10 meter. And this sphere, the positive charge is uniformly distributed. And he proposed that the electrons are embedded in this positive sphere in such a way to gain the maximum stability. So, few key points of this model is that mass of the atom was assumed to be uniformly distributed over the atom. So these electrons are embedded in such a way that it created uniformity. And also this model was able to explain the overall neutrality of the atoms. So Thomson's this is the model that is proposed by the Thomson, and this positively charged spheres with electrons embedded in it looks like plum pudding, raisin pudding, and watermelon. So all of these names were given to this model. But this model was not consistent with the result of some experiments that was performed later. Like after he proposed this model, then various scientists from all over the world carried out certain experiments in order to prove that if he was right, that Thomson was right or wrong. So the different scientists carried out different experiment which was not consistent with his idea of the model of atom. So further, we'll be talking about the Rutherford's atomic model. Rutherford, along with his students Hans Geiger and Ernest Marson, proposed Rutherford's nuclear model of atom. So this is the pictorial representation of Rutherford's famous alpha particle scattering experiment. This yellow one is the gold foil, which is very thin. Approximate thickness is 100 nanometers. A stream of high energy alpha particle from a radioactive source is directed towards this thin foil. So this thin gold foil had a circular fluorescent zinc sulfide screen around it, just like we studied in cathode ray tube experiment by J.J. Thomson. So whenever a alpha particle strikes the screen, there is a tiny flash of light which is produced at that point. So, and this is the molecular view of the gold foil. So this arrow represents the beam of alpha particles flowing, and these yellow ball-like circular structures represents the deflected alpha particles, and it can be seen that most of the alpha particles gets to the thin gold foil undeflected, and very few of them gets deflected by really small angles. So, so the result of this scattering experiment was quite unexpected and also contradicted Thomson's atomic model. So we studied Thomson's atomic model, and there we saw that the mass is uniformly distributed in that positively charged sphere. So if that was the case, then this alpha particles has enough energy to pass through such a uniformly distributed mass. Okay, so it is expected that the alpha particles will only slow down or change the direction, like in a very small angles. But it was observed from this Rutherford's very famous scattering experiment that most of the alpha particle passed through that gold foil undeflected. Okay, and a very small fraction of the alpha particle was deflected only by very small angles, and very few alpha particles, like 1 out of 20,000 alpha particles that was flowing, bounced back, that is very much deflected by nearly 180 degree, so just got back. So after this experiment, Rutherford, along with his students, concluded certain things, and so these are the conclusions. And so most of the space in the atom is empty because we saw that most of the alpha particles passed through the gold foil undeflected, and a very few positively charged alpha particles. We all know that alpha particles are nothing but the positively charged particles. So the deflection, very small alpha particles got deflected, and that deflection maybe because of the enormous repulsive force, which shows that the positive charge of the atom is not spread throughout the atom as presumed by the Thomson. So the positive charge must be concentrated in a very small volume, so that repelled and deflected the positively charged alpha particles. So instead of like a fully positive charged sphere as described by Thomson's, it is not the case. So it is a very small concentrated positive charged um, volume that repels and deflects these positively charged alpha particles flowing through the gold foil, and it is, and rather than like being throughout. And calculations by Rutherford showed that the volume occupied by the nucleus, that is the positive charge entity, is negligibly small as compared to the total volume of the atom. For example, the radius of the atom is about 10 to the power of minus 10 meters, while that of the nucleus is 10 to the power of minus 15 meters, like very small in comparison to the whole of the atom. So after all of these experiments and conclusions, Rutherford proposed a nuclear model of atom. So according to this model, the positively charged, the positive charge and the most of the mass of the atom is concentrated in extremely small region, and this very small portion of the atom is called the nucleus by Rutherford. So the term nucleus is coined by Rutherford, and he states that in the atom जो सबसे ज़्यादा concentrated part है, जो डीप जो डेंसली कॉन्सेंट्रेटेड है, वो बहुत ही छोटा है पहले तो पूरे एटम के रिस्पेक्ट में, और वो बीच में है, मतलब इन द मिडल है वो, और most of the atoms it is empty, only the most of the concentration is, the concentrated region is extremely small and it is in the middle of the atom, and the nucleus is surrounded by electrons that is moving around the nucleus. So the nucleus is positively charged and this electron entities are moving around the nucleus in a defined orbitals. So according to the Rutherford model, basically resembles a solar system where there is a sun is the nucleus and the planets are the electrons. And these electrons, that is the negatively charged particles, and the protons, that are the positively charged nucleus, they are held together by the electrostatic forces of attraction. So this is basically the model of the Rutherfords, and it was very famous that time. And he actually, when you come to realize that, he actually proposed it quite well, because many things, many points is correct, but also there are some uh, downfalls, pitfalls in this models as well, which will be discussed later in the slide. So now we will be studying about atomic number and mass number. So what basically are these two entities? So atomic number क्या होता है? It is equal to the number of protons in the nucleus of an atom, which is also equal to the number of electrons in a neutral atom. इसको explain करते हैं. प्रोटॉन्स जो होता है वो पॉजिटिवली चार्ज एंटिटी होता है और वो न्यूक्लियस में होता है. तो प्रोटॉन्स न्यूक्लियस में होता है और किसी भी न्यूट्रल एटम के लिए इलेक्ट्रिकल चार्ज बैलेंस करने के लिए जितना नंबर ऑफ प्रोटॉन होगा उतना ही नंबर ऑफ इलेक्ट्रॉन भी होगा. एटॉमिक नंबर जिसको हम लोग Z से रिप्रेजेंट करते हैं वो होता है इज इक्वल्स टू द नंबर ऑफ प्रोटॉन्स इन द न्यूक्लियस ऑफ एन एटम. और एटॉमिक नंबर को हम लोग ऐसे भी बोल सकते हैं इट इज इक्वल टू द नंबर ऑफ इलेक्ट्रॉन्स इन अ न्यूट्रल atom. It has to be neutral atom, because if the atom is somewhat charged, then these two numbers, that is the number of electrons and the number of protons, won't be same. Okay, and the second term, that is the mass number. So we have discussed that the dense part of the atom is nothing but the nucleus, and the nucleus consists of protons and neutrons. So the mass of an atom is nothing but the mass of the nucleus. So mass number is equal to the number of protons, that is represented by Z, that is the atomic number as well, plus the number of neutrons, which is represented by small n. So mass number A is equals to the atomic number plus the number of neutrons. So now let us talk about isobars and isotopes. We have heard this terms like quite a lot of times. So what basically are isobars and isotopes? This particular thing is the elemental symbol of an atom, where X represents the initials of the atom, and A and Z represents the mass number and the atomic number. So isobars are the atoms with same mass number but different atomic number, whereas isotopes are the atoms with different mass number but same atomic number. So basically isotopes and isobars are just opposite to each other. One has same atomic number and the other has same mass number. So for example, let us talk about hydrogen atom. So we all know that hydrogen atom, there is one proton there, but this is not the truth. Okay, the reality is that there are 3 isotopes of hydrogen present in the atmosphere. Those are hydrogen, deuterium and tritium. So the hydrogen is and all of these 3 are represented as these are their elemental symbol. This is for hydrogen, this is for deuterium, and this is for tritium. So this hydrogen that we all know is very common. It constitutes the total 99.9% of the total hydrogen atoms present in the atmosphere, and the rest percentage is the mixture of deuterium and tritium. So hydrogen has atomic number of 1, and deuterium and tritium also has atomic number of 1. So all of these three are what? They basically have same atomic number, and same atomic number means these three are isotopes to each other. They have got different mass number, right, which is represented as the superscript of the in the elemental symbol. So they have got different mass number. In proton, it has one. In case of hydrogen, it has only 1 proton and 0 neutron, and hence the mass number is 1. In case of deuterium, there is 1 proton and 1 neutron, and hence the mass number is 2. In case of tritium, there is 1 proton and 2 neutron, which constitutes the mass number of 3. A very important sentence is that all of these isotopes, they have what similarity isotopes have? They have same number of same number of protons. Okay, so the chemical properties of atoms are controlled by the number of electrons. So number of protons equals to number of electrons in a neutral atom, right? So all of these have same number of protons, meaning that all of these have same number of electron as well. So basically the chemical properties of any atom is governed by the number of electrons it has. So which means that all the isotopes has same number of proton and same number of electron. So this means that all the isotopes have similar chemical properties. Okay, so neutron has nothing to do, it has very little effect on the chemical property of an element. Therefore all the isotopes of a given element show same chemical behavior. Until now, whatever we have studied in the previous slides, so we are going to take the problem solving thing right now. So all of these questions are taken from the NCERT exercise, and these questions from 2.1 to 2.4 constitutes of all the syllabus that I have already covered in the previous slides. So let's go to the solving part. So the first question, that is 2.1, the first part is the calculate the number of electrons which will together weigh 1 gram. So we know that 1 gram equals to 10 to the power of minus 3 kgs, and mass of one electron, that is represented by Me, equals 9.1094 into 10 to the power of minus 31 kgs. So from the unitary method we can solve this question, like number of electron in 1 gram into mass of one electron will be equal, it should be equal to 10 to the power of minus 3 kg as stated by the question. So here we have taken the number of electron in 1 gram to be n. So n into the mass of one electron equals 10 to the power of minus 3 kg, which makes, by solving this, we will get the answer of number of electrons in 1 gram to be 1.097 into 10 to the power of 27. In the second part of this question, it has asked to calculate the mass and charge of 1 mole of electron. So first of all, we all know that 1 mole of electron, it is equal to the Avogadro's constant, which is equals to 6.022 into 10 to the power of 23 electrons. So we already know that the mass of electron is equal to 9.1094 into 10 to the power of minus 31 kgs. So therefore, from unitary method again, mass of 1 mole of electron will be equal to mass of 1 electron into number of electrons in 1 mole. So that is equals to 9.1094 into 10 to the power of minus 3 into 6.022 into 10 to the power of 23 kg, which is equal to 5.485 into 10 to the power of minus 7 kg. The question has also asked for the charge of 1 mole of electron. So which can be solved by this equation. Charge of 1 mole of electron is equals to number of electron into charge of 1 electron. So we already know from the previous slides that the charge of 1 electron is equals to minus 1.6022 into 10 to the power of minus 19 coulomb, and number of electron in 1 mole is equal to 6.022 into 10 to the power of 23. We just have to multiply these two quantities, which will give the answer of as 9.6494 into 10 to the power of 4 coulomb per mole. Question number 2.2, first part, asks us to calculate the total number of electrons present in 1 mole of methane. The total number of electrons present in 1 mole of methane. So methane is CH4. So number of electrons in 1 molecule of methane is equals to 6 for carbon and 4 into 1 for hydrogen, that equals to 10 electron in one molecule of methane. So now for 1 mole we know that it is equal to Avogadro's number. So that is equals to 6.022 into 10 to the power of 23 molecules. Therefore, number of electron in 1 mole of methane, as asked by the question, is equals to the number of electrons in 1 molecule of methane into number of molecules in 1 mole. So that is equals to 6.022 into 10 to the power of 23 into 10 electrons, which gives this as an answer 6.022 into 10 to the power of 24 electrons. In the second part of this question, it has asked to find number A, the total number, and number B, and the total mass of neutrons in 7 milligram of 14C, and it has also given the mass of one neutron. So first of all, 14C, in 14C, number of neutron is equals to how much? So we know that the atomic number for carbon is 6 and the number of neutrons is equals to the mass number minus the atomic number. So that is equals to 14 minus 6, that gives 8. So the number of neutrons in one molecule of 14C equals 8. Here 14, and we know that 14C has 14, the mass number has 14. So in that 14 gram, the number of molecules of 14C is 6.022 into 10 to the power of 23. So the question has asked for 7 milligram. So from just a simple unitary method, we can calculate the number of molecules in 7 milligram of 14C, and this is the calculation that will be done, and we'll get the number of molecules of 14C in 7 milligram as 3.011 into 10 to the power of, it will be 20 here. By mistake I wrote 23. So it will be 20 here. Now the number of molecules in number of neutrons in 7 milligram of 14C is equals to 8, which is the number of neutron in one molecule of 14C. So 8 into 3.011 into 10 to the power of 20, which will give the answer as 2.4088 into 10 to the power of 21. In the B, they have asked to calculate the mass of neutrons in 7 milligram of 14C, and also they have mentioned in the question the mass of one neutron. So from a simple unitary method, we can find out the mass of neutron in 7 milligram of 14C by just multiplying the mass of one neutron by number of total neutrons that we have calculated already in the first part. So that is equals to 1.675 into 10 to the power of minus 27 kg into 2.4088 into 10 to the power of 21. That gives the answer as 4.03474 into 10 to the power of minus 6 kg. In question number 2.2, third part, so they have asked that find number A, the total number, and B, the total mass of protons in 34 gram of ammonia at STP. And also they have asked that will the answer change if the temperature and pressure are changed. So this question is actually similar to their second part, okay, but they have asked another sub question, and that is will the answer change if the temperature and pressure are changed. So for this particular part, the answer is no. First of all, we know you have to understand what is STP. STP is standard temperature and pressure. This is regarded as the standard temperature and pressure. So they have asked that if we deviate from this particular temperature and pressure, so will this number of protons and number of mass will change or not? So the answer is no, they will not change, because in any temperature and pressure, the number of protons and the mass of it is actually constant for a given nuclei. So coming to the question A part, we need to calculate the total number of proton in 34 milligram of ammonia. So again approaching the question in the similar manner. So number of proton in one molecule of ammonia we need to calculate first of all. So ammonia is 1 nitrogen and 3 hydrogen. So the number of proton is nothing but their atomic number. So atomic number of nitrogen is 7 and atomic number of hydrogen is 1. So 7 plus 3 into 1, that gives 10 protons. So there are 10 protons in one molecule of ammonia, and uh, the mass number of ammonia is 17 gram. So and that 17 grams constitutes to Avogadro number molecule of ammonia, that is 6.022 into 10 to the power of 23 molecules of ammonia in 17 gram of ammonia. So the question has asked for the number of protons in 34 milligrams. So let us calculate the number of protons in 34 milligram. So by doing this simple unitary method, we can calculate the number of molecules in 34 milligram by dividing by 17 gram and multiplying by 34 milligram. So this gave the answer as for 12.044 into 10 to the power of 20 molecules of ammonia in 34 milligram. Okay, so the question has asked for the total number of protons. So the total number of protons will be equal to number of protons in one molecule of ammonia multiplied by the total molecules of ammonia. So that gives us 12.044 into 10 to the power of 21 protons as the answer. In the second part, they have asked for the total mass of proton, but they have not mentioned the mass of proton. So this actually tells you guys that you need to memorize this mass of proton, mass of electron, mass of neutrons also for some matter. So if you memorize this, because these are important numbers, you need to learn in order to solve the question. So in order to calculate the total mass of proton, we can do that by multiplying the total number of proton into mass of one proton in 34 milligram of ammonia. So that is equals to 12.044 into 10 to the power of 21 into 1.6726 into 10 to the power of minus 23 kg. So that is equal to 20.1809 into 10 to the power of minus 6 kg as answer. Question number 2.3. How many neutrons and protons are there in the following nuclei? And they have given total 5 elemental symbol, and you need to calculate the you need to calculate the neutrons and the protons. So whenever you get the elemental symbol, first of all you need to calculate the number of proton, because you don't need to calculate, that is already given. We all know that number of proton is equals to the atomic number of any atom, and in this elemental symbol the subscript is the atomic number and the superscript is the mass number. So directly since atomic number is given, so directly number of proton is already given. So number of proton is equals to the atomic number of any atom, and that is here equal to 6. And for neutron you just have to do a simple subtraction. You need to subtract the number of proton from the mass number, and the mass number is given in the subscript, so that is equal to 13 minus 6, that is equals to 7. For this 1608, here also number of proton is given as the atomic number, so that is equals to 8, and for neutron you need to subtract 8 from the mass number that is given in the superscript. So 16 minus 8 is equals to 8. So here you can see that the number of proton is equal to the number of neutron, but it is not the case always, as we have already seen in this one also, and in the further examples also you will see there is nothing like that. The number of proton will be equal to number of neutron. It is a myth. So this question 24 mg 12. So here it is the number of protons is equals to 12 as given by the atomic number, and number of neutron is equals to 24 minus 12, which gives 12 as the answer here. The next one is the 56 iron 26. Here also proton is equals to 26 because 26 is the atomic number and atomic number is equals to the number of protons only. And for neutrons you need to subtract mass number by the atomic number, so that is equals to 30. So in the last question, proton is 38, again similar way, and neutron is equals to 88 minus 38, that is equals to 50. So let us move to the next question, 2.4. In this question they have asked to write the complete symbol for the atom with the given atomic number Z and atomic mass A. So actually in the question, which I have not written here but you guys can see in the book, so they have given atomic number and the atomic mass of the atoms. You just need to recognize those atoms and write it in the elemental symbol. So from the number of proton, we know that the number of proton, that is A, that is also equals to A, that is at the atomic number. So from the atomic number you can know what is the element. So for 17 it is chlorine, 1735 is chlorine, and similarly for 92 is uranium, which has a mass of 233. It is one of the isotopes of uranium. And for 4 it is beryllium, which has the mass number of 9. So for this video, this is what I covered. So structure of atom is a big chapter and I will be covering it in parts. So this was the first video, and the rest, again I have divided the whole this chapter into small subparts because lengthy videos are difficult to read. So I have divided it into small videos, and this is the first part. I hope you all understand what I taught.